Today's lesson is sourced from Chapter 4 of Mechanics of Materials. This video is part 1 of the lesson, in which we'll review the key concept. Stay tuned for part 2 in the next video, in which we'll solve an example problem. We'll start by bridging the gap in our understanding of axial loads. In this chapter, we'll combine what we know about stress and strain to see how they're related and what they reveal about how a material behaves under loading. Let's start off by defining an equation for elastic deformations. If a bar is axially loaded, we can find the displacement of one end of the bar relative to the other end. We can do this by rearranging the equations for stress, strain, and Hooke's law. If you haven't checked out the key concept videos for Chapter 1 and 2, feel free to review those and then come back to this one once you get yourself up to speed. We know that the average normal strain equals the change in length over the original length. Notice that we've replaced L final minus L initial with lowercase delta, which means displacement. Then we'll just rearrange the equation to solve for delta. We also have the equation of average normal stress to the right. The average normal stress is equal to the internal resultant normal force divided by the member's cross-sectional area. Lastly, we have Hooke's law, which is stress equals the modulus of elasticity times strain. We'll rearrange it to solve for strain so that it reads stress over the modulus. Then we can replace sigma by n over a. Next, we'll multiply both sides by L initial so that we can replace the left side of the equation by delta. So our final equation should read delta equals n times L initial over a times e. Before we move on, let's take a moment to define each of those variables. As you can see, the displacement of a section of a specimen is denoted by delta and is dependent on 4 different quantities: the internal axial force at the section, which is n, the original length of the section, which is L initial, the cross-sectional area of the section, which is A, and the modulus of elasticity of the material, which is E. This specific version of the formula is only applicable when all the variables of the equation are constant. In other words, the specimen must be homogeneous in material to keep a constant modulus of elasticity, and it must also be uniform in length and cross-sectional area. Finally, the material must have a constant external force applied to it, which means that it also has a constant internal force of N. But again, this specific version of the formula is only applicable under these specific conditions. What happens if the bar looks less like the diagram on the left and more like the diagram to the right? In this case, the bar has different cross-sectional areas, lengths, and internal forces. We can actually adapt the displacement equation to each section of the bar, then just sum those displacements all together. You can see the final equation on the left. One last thing to note is sign convention. We'll take the internal axial force and displacement to be positive if they cause tension and elongation, and we'll take the values to be negative if they cause compression and contraction. Great. Now let's take a look at how we can use this displacement equation. If a specimen is subjected to a complicated loading, we can subdivide the load into components to find the stress or displacement at a specific point in the specimen. This is called the principle of superposition. It basically states that if we subdivide the loads, the resultant stress or displacement is a sum of all the component stresses or displacements that make it up, if those separated loads were to have been applied independently. But the principle of superposition has 2 conditions that need to be met if we use it. First, the loading N has to be linearly related to the stress or displacement. Second, the loading cannot significantly change the original geometry of the member. If those 2 stipulations are satisfied, then we can use the principle of superposition as it is shown pictorially on the left. You can see how the total loading is subdivided into F1 and F2, which cause a displacement of delta 1 and delta 2, respectively. If the component loadings are added up using the principle of superposition, then you can also add up the component displacements to get a total displacement of delta. Nice work! Our next key concept is the compatibility equation. We formulate a compatibility equation whenever we have statically indeterminate problems. But what does it mean to be statically indeterminate? Well, it's exactly what it sounds like. It means that it can't be solved with just the equations of equilibrium. In other words, there are more unknown reactions than the three equations we're used to solving with. In cases of statically indeterminate structures, we need to come up with a fourth equation called the compatibility equation. There's actually no defined formula of compatibility. Instead, we take a look at the load displacement relationship to tell us if and how the bar can deform at its supports. The method we'll use to formulate our compatibility equation is called the force method of analysis. If you think back to statics class, you may remember that we used to assume that all members were rigid, so we didn't take deformations into account. But now that we've learned the displacement formula, we can use it in mechanics of materials. More specifically, we'll use the force method of analysis for axially loaded members, which basically involves using superposition of the forces acting on the free body diagram. Check out the image to the left. Notice that there is an external force acting at C. You can also see that the bar has fixed supports on both of its ends, so there should be no net displacement. How can we have an external force but no displacement? That's when the force method of analysis comes into play. First, let's choose one of the supports as a redundant and hypothetically remove it for the time being. In this case, let's take out the axial force exerted by the fixed support at point B. If you look at the middle image, you'll find that the 500 Newton load at C causes point B to be displaced downward by a length of delta P. Now let's bring back the axial force at B and consider it in isolation. This displacement will be equal in magnitude and opposite in direction of delta P. In other words, the reactionary force FB counteracts the downward displacement of delta P with an upward displacement of delta B. We see this play out in our compatibility equation for this situation. Remember how we said that there should be no net displacement because of the fixed supports? We'll get a positive downward displacement of delta P minus a negative upward displacement of delta B, which will sum to 0. Okay, I know that was a lot, but we only have one more key concept to go. Let's talk about thermal stress. Think about how heat changes the size of an object. An increase in temperature usually correlates to expansion, and a decrease in temperature causes contraction. Usually, the change in temperature and the length of an object are linearly related. We can see this in the equation for thermal displacement, which is delta equals alpha times delta T times L. Delta represents the change in length of the bar, delta T is the change in temperature, and L is the original length of the bar. Alpha is a constant called the linear coefficient of thermal expansion, and it's an inherent property of the bar's material, kind of like the elastic modulus is also. The thermal displacement of a statically determinate member is easier to calculate since the member is free to expand or contract at its ends. But for statically indeterminate members, the constraints at its members don't allow for these thermal displacements, which then causes thermal stresses in the material. This is why traffic bridges have expansion joints. The joints help reduce any thermal stresses and accommodate for any thermal expansion of the deck. We made it! I hope this lesson helped you understand a little bit more about axial loads and displacements. Stay tuned for the next video, where we'll solve an example problem that incorporates several of the concepts we just learned. Thanks for watching!